Hi, I'm Mrs. Bricky, and this is lesson 2 from Unit 7 for Math 2. So today we're going to be graphing quadratic functions, and we'll learn what quadratic means. The very most basic quadratic function is the function y equals x squared. So last class we graphed absolute value functions, and they had a V shape. Let's figure out what shape a quadratic function has. So for our table of values here, we're going to just be squaring each of those inputs. So our function is that our output is just the number squared. So if I have a -3 and I square it, I'm going to get 9 as my answer. -2 squared, which is -2 times -2, that gives me 4. -1 squared gives me +1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So if we plot those points, we'll be able to see the shape of a quadratic function. So -3, 9. -2, 4. -1, 1. We have 0, 0, the origin. 1, 1, 2, squared is 4. And if we included 3, 3 squared gives me 9, so we're back up here. So this shape, you can see, is somewhat similar to a V, but last class we had, straight edges on our shape. And you can see that this is not going to be the kind of shape, that has a straight edge. We have these curvy edges. So sometimes a student will say it's like a U shape. In math, this shape actually does have a name. The shape of this function is called a parabola. And all quadratic functions will have the shape of a parabola. Just like with our absolute value functions, we can have them stretched or moved around, translated. So let's look at another quadratic function. This time we are still going to use a table, but then we'll look at a pattern for graphing these a little bit faster, just like we did with absolute value functions. Okay, so we're going to sub in these values, -2, -1, 0, 1, 2, and 3, into our function, and our function is f of x is equal to our quantity of x minus 2 squared, and then subtract 5. So our first input, -2 minus 2 squared minus 5. You are welcome to use a calculator to do that, or you can kind of think through it on your own. This gives us, let's see, I think it's 11, but let me just double check it in case I'm doing my math bad today. Yeah, 11. So the first point I'm not even able to plot because my coordinate plane over here does not go up to 11. That's okay. Sometimes you're not sure what numbers you should use to get started, and so then you just work on it until you get some values that work. Okay, let's see. So if we sub in -1, our output is 4. So I can add this point to the graph. -1, +4 is right here. If I sub in 0, 0 minus 2 squared minus 5 is 4 minus 5. That's -1. So 0, -1. If we sub in 1, that is -4. Now we're subbing in 2. 2 minus 2 is 0, so this is 0 squared minus 5. That's -5. And 3 minus 2 squared minus 5 gets us back to -4. And then let's go ahead and add 4 to our table and sub in 4. 4 minus 2 squared minus 5 is -1. Okay, so we've got one more point here. So you can see we have that same parabola shape. If we subbed in 5, we would get 4 again. So we've got this parabola shape. Woo! So that curved shape of the parabola is a result of the squaring process. Our function was, or our parent function x squared, it has this operation of squaring. So the reason that we get this shape is because of how perfect squares change. 0 squared is 0 and 1 squared is 1. So the first change is that we've gone up 1 between those two perfect squares. The next perfect square, 2 squared, is 4. So after we've gone up 1, our next change is that we go up 3. And then 3 squared is 9. So our next change from 4 to 9 is that we've gone up 5. And then the next perfect square is 4 squared, which is 16. And so then we've gone up 7. So a parabola is growing according to these numbers, 1, 3, 5, 7, if we had room on our graph. So we kind of just call that the 1, 3, 5 pattern for a parabola. So we first go up 1 and then over 1. Then we go up 3 over 1, and then we go up 5 over 1. So each time, you can think of these as fractions over 1, like when we do slopes. So we don't go like up 3 over 3. We go up 3 over 1. So 1, 3, 5 is the pattern that we use to help us get this U parabola shape. A parabola is symmetric because if we have negative numbers and square them, we also get that positive result. So both 1 squared and negative 1 squared give me the same result, which is 1. Both negative 2 and 2 squared give me the same result, which is 4. So we have some symmetry that happens on these parabolas. So we get the same height here and here. We get the same height here and here. So when we graph parabolas, we don't want to have to go through this process every single time. It's a lot to evaluate the output for each of those inputs. And we know what our shape is going to be. We know it's going to have this parabolic U shape. So instead of using a table of values each time, we want to use the form of the equation and our knowledge of that shape to do the graph a little bit faster. The way that we're going to graph these parabolas is very, very similar to the way that we graphed absolute value functions. The main difference is just the shape. But we are still going to see the vertex of the parabola, and it is still called a vertex. We'll see the vertex of the parabola with the x and that k value at the end. And then we'll look at the stretch, the vertical stretch, which changes the curvature to be that coefficient a at the beginning. So the reason we know that this, if this equation, the reason we know that it's a parabola shape instead of a V shape is because of the power of 2. If we had absolute value bars instead of a power of 2, we know that that's going to give us a V shape. When we see the parentheses with this power of 2 on that x minus h, we know that it's going to be that parabolic shape. Okay, so let's try graphing a couple of these. So our first parabola is y equals x minus 2 quantity squared plus 1. So just like with our absolute value functions, we want to identify the vertex by looking at these two numbers on our function. So our vertex here is 2, 1. And just like with absolute value functions, we have to remember that we've got a sign change compared to what we see in the equation. So if we see an x minus 2, we know that the x coordinate of the vertex will be positive 2. For the stretch factor, we look for that coefficient in front of the x squared. So on this one, we just have a stretch factor of 1. That means we're just going to do our basic 1, 3, 5 pattern. So from our vertex, we're going to go up 1 over 1. Then we're going to go up 3 over 1. And then if we had space, we would go up 5 over 1. That establishes one side of the parabola. So now we need to do that pattern backwards. To get the other side, we need to sort of reflect it. Up 1, up 3. And again, if we had space, we would go up 5. So here's our little parabola. Try not to make it sharp like a V. Try to get it to be a bit curved. This is not reflected vertically, so some of our parabolas are going to go, we would say maybe opens upward. This is not reflected. If it opens downward, we would say that this is reflected vertically. Because our graph right here is not reflected vertically, that means that we have a minimum. The minimum of this, the minimum value of this function is 1. And again, when we're reporting mins or maxes, we want to report the y value. So we talked about that parabolas are symmetric. So the axis of symmetry is like an invisible line that would cut that parabola right in half. So this one has an axis of symmetry of x equals 2. Okay, let's try another parabola. This one is y equals negative quantity x plus 3 squared plus 4. Again, the power 2 tells me it's going to be a parabola shape. The vertex is going to be at negative 3, 4. So again, we've got the sign change to watch out for here, and then just the regular 4 at the end there. So our vertex is at the point negative 3, 4. And our stretch factor is negative 1. We don't see the 1. We just see the minus symbol there, but that means it's a stretch of negative 1. Now, when you have a stretch for this pattern, whatever the a value is at the front, for us it's negative 1, you multiply that by the 135. So if it's negative 1, our pattern becomes negative 1, so down 1 over 1, negative 3, negative 5. We would just take that 135 and multiply each of them by negative 1. So we're going to go down 1, and then down 3, and then down 5. So down 1 over 1 puts us here, down 3 over 1 puts us here, and then down 5 over 1 puts us here. So we need to just sketch the other side of that parabola as well. So down 1, down 3, down 5. So here's our points to use to help us get that sketch nice. And just, do your best with the sketch. They're not always perfect, but just make it, as good as you can. So this one was reflected vertically. It opens downward. And because it got reflected and it's opening downward, it has a maximum value. And the maximum value of this function is 4. The axis of symmetry of this function, so if we think about that imaginary line of symmetry that cuts that parabola right in half, that would be x is equal to negative 3. Now, when we're writing our axis of symmetry, we are giving the equation of this vertical line. So it is important that you have the x equals negative 3. You don't just want to write the number negative 3. For min and max, you are just giving a number, like that is the highest the function goes. And it is okay to just list it as a number 4, but for axis of symmetry, we do want to list x equals negative 3. Okay, let's try a couple more. Both of these have stretches, so we'll see how a stretch of negative 2 and a stretch of positive 2 affect our parabola. So for our first function here, y equals negative 2x squared plus 5, you'll notice that that x is not really even in parentheses. We don't have we don't have any shifting to the left or right for our vertex. The vertex is at 0, 5. So notice that this is different than if we had something written like this. -2, if it had parentheses around the x plus 5 and then the squaring, that would be much different than what we have. So our vertex is at 0, 5. 0, 5 is right here. The stretch factor is -2. So that means we need to take that 1, 3, 5 pattern and multiply it by -2. So our first bit of our pattern is going to be -2. And if you want, you can think of this as kind of distributing. Each of these numbers gets multiplied by -2. So it's -2, -6, -10. So we're first going to go down 2 over 1. Then we're going to go down 6 over 1. And almost always we don't have room to go down an additional 10. So we almost always only use the -2, -6. Here's the other side of that parabola to make it nice and symmetric. So multiplying it by -2, the negative makes it open downward. And the stretch of 2 kind of makes it more narrow, is how it feels when you're sketching it. It's just growing faster. Okay, so this is reflected vertically. It has a maximum value of 5. And the axis of symmetry of this equation, if we think about that imaginary line that cuts that parabola in half, it's just x equals 0. Okay, last graph. Our function is y equals 2 multiplied by an x minus 4 squared, and then subtract 6. So our vertex is at 4, -6. That's way down here. The stretch factor is 2. So we need to take that 1, 3, 5 pattern, and we need to double it all. So our pattern is going to be 2, 6, and 10 if we could fit it. So up 2 over 1, up 6 over 1, and then in theory we would go up 10. Again, it hardly ever will fit. Every once in a while you might have a coordinate plane that is big enough that it has enough room. Okay, so here's my parabola. Again, when we have a stretch of 2, it kind of makes it seem more narrow and skinny. So this one is not reflected vertically, or I guess I should just say no. This function has a minimum value, and that minimum value is -6. And then our axis of symmetry, our line of symmetry here, is at x equals 4. Okay, if you are watching this because you missed class, you have enough information now to work on the front side of the practice. You can pause the video and do that if you want. Okay, now we're going to just try to do that process backwards. If we have a picture of the graph, can we give the equation? I think it's a great idea always to write down the vertex, especially if you find that you're making mistakes when you do this. Sometimes just writing down that vertex as a point helps you translate it into the equation better. And then for the stretch, you kind of have to look at the pattern on the parabola and see, like, how much is it going up before it goes over 1? Well, if I go over 1, I'm right here, so I'm going up 2 over 1. And then my next height is way up here. So I went up 2 and then up 6. So that means the stretch factor is 2, because our base pattern is 1, 3, 5. So our 1, 3, 5 pattern has gotten doubled. So we're ready to write the equation now. Don't forget the y equals. Our stretch factor is 2. It's going to be x minus 3. And then don't forget the power of 2. The power of 2 is so important here. We don't want to write something like this, because that actually would end up being a line. The power of 2 right here is super, super important. Okay. So don't forget your power of 2 for your parabola, and then plus 1 for that height of 1 on the vertex. Okay, so for domain and range, parabolas, sometimes people get a little bit confused about the domain of parabolas because they don't go out to the left and to the right as quickly as an absolute value function, but they do still have a domain of negative infinity to infinity. They do still have a domain of all real numbers. And remember, you can use this symbol for all real numbers if you like. So both this symbol for all real numbers or writing it in interval notation as negative infinity to infinity, those are both acceptable for the domain of this graph. For the range of this graph, just like with our absolute value functions, the range is limited. So for the range of this particular parabola, our lowest value is 1, and it goes up forever, so 1 to infinity. We do want to include the vertex, so we use a bracket on the 1. Let's practice that again. So here's the vertex of this parabola. It's at the point -4, 6. Looking at the stretch, it looks like this thing is going down 1, and then down 3, and then down 5. So it's going down 1, down 3, down 5. Our stretch factor that we see in the equation is -1. So our equation is y equals negative. You can put a 1 there if you want, or you can just put that negative symbol. -1 times by x plus 4. We've got the sign change showing up on that h, and then plus 6. The domain of this parabola and the domain of all parabolas, negative infinity to infinity, or you can use the symbol for all real numbers. Our range, remember that we need to write our range from lowest to the highest value. So our range is from negative infinity. This is the negative side of the y-axis. So from negative infinity up to 6 with the bracket on the 6. Okay, so we are going to write the equation of this last graph, but we're also just going to answer a few questions about it. Our first question is, what does this function have a maximum or minimum value, and what is it? Well, for this particular graph, we have a minimum value of -9. The next question asks us for the x-intercepts. So remember that x-intercepts are where the function crosses the x-axis. So in this case, we have 2 x-intercepts. The x-intercepts are -4 and 2. Sometimes people like to write these in point form. If you do, they would look like this. Our next question asks us the y-intercept. So we are looking for where does the graph cross the y-axis. This is not asking us for the location of the vertex. It's asking us for the y-intercept. So the y-intercept is at -8, or in point form, this would be the point 0, -8. Okay, our next question asks us to evaluate or find f of -2. So we're looking for the y value that goes with an x value of -2 for this graph. So here's the x value of -2, and we can see that the y value is right here at -8. So our answer to this question, number 4, is also -8. Question 5 is different from question 4. Question 4 asked us to find the y value that went with an x value of -2, but question 5 is saying, can you find x when or if f of x is equal to -5? So our -5 here is a y value, and we're looking for the associated x values. Well, a y value of -5 is here, and we actually can see that we have 2 spots on the function where the y value is equal to -2. We have, sorry, -5. We have 1, -5, so that's an x value of 1, and we have -3 associated with -5 as well. So our 2 answers for x are 1 and -3, and you should look for both of them on a parabola. Okay, finally, our last question here asks us to write the equation. For the equation, we use the vertex. So this function has a vertex at -1, -9. And if we check the stretch really quick, it's just a regular 1, 3, 5 pattern. So our equation would be y is equal to, we're going to have x plus 1 squared and then -9. Okay, so today we learned all about graphing parabolas. Last time we learned about graphing absolute value functions. They have a lot in common. We just find the shape of the graph a little bit differently, whether it's the curved parabola or the flat edges of the V. So let's do a couple little problems about transformations really quickly. These two functions transform exactly the same way. So the a value that's at the front is going to be the vertical stretch, which either changes the curvature or the slope of the function. The h value that's with the x is going to be the horizontal translation, which is the movement to the left or to the right of the vertex. And then the k value, which is the constant at the end, is the vertical translation, and it is going to tell you about if the function is shifted upward or downward. And so we are just on these problems going to describe the horizontal and the vertical translations. So looking at this function, I can see that the vertex is at 1, 4. That means that this was shifted to the right by 1 unit, and it was shifted up 4 units. And again, we're always sort of comparing to the origin. So, on a coordinate plane, our function, this one happens to be a parabola, is, usually has the vertex at the origin, but our function f of x right here, it was shifted to the right 1 unit and up 4 units. It also has a stretch, but this question is not asking us at all about the stretch. Okay, so the next question, g of x is equal to -1/2 times the absolute value of x plus 6. Again, this one would be a V shape, but if we're asked about the translations, we don't have to really worry about the shape. We have an x plus 6 right here, so this one would be shifted to the left by 6 units. Sometimes it helps people if they write down the vertex. So we've gone from the origin back 6. And this one does not have a vertical translation. Again, if we had a super rough graph of this, it would be over here at -6, 0, and it happens to go downward.